Hello, everyone. Thank you for joining us. We are going to give it another minute or so here to let everybody join, and then we will get started. All right, it is that time, so we're going to go ahead and get started. Hello, everybody. On behalf of the Environmental Finance Center Network, welcome to our webinar today on Operator Certification, Activated Sludge Components and Operation, Part 1. My name is Maya Bani from the Syracuse University Environmental Finance Center. And just before we begin here, we're going to go over a few housekeeping items and then we can get started. During the training today, everyone will be kept on mute to ensure audio quality. If you have a question, please type it into the GoToWebinar question dialog box anytime throughout the session. We will be saving your questions for a facilitated Q&A session at the end of the presentation. After the webinar, you will receive a follow-up email that includes a link to the recording and any other information you may need. You can also download the slides from today in the Handouts tab in your GoToWebinar control panel. This session has not been submitted for pre-approval of continuing education credits, but eligible attendees will receive a certificate of attendance for their personal record. To receive a certificate for this session, you must attend for the entire session and register and attend individually using your real name and unique email address. Certificates will be sent via email within 30 days of this webinar date. If you have any questions or need assistance, please contact us at smallsystems@syr.edu. All right, and now just for a little bit about us, the Environmental Finance Center Network provides training and technical assistance to small water and wastewater systems in all U.S. states and territories through our building technical, managerial, and finance capacity programs. If your community or utility needs assistance with drinking water or wastewater system management, please feel free to contact us through our request form, which I'll be sharing shortly in the chat. And on that note, we can get started. I would like to introduce our presenter today, James Markham, a research engineer from the Southwest Environmental Finance Center.
All right, let's just get ourselves transferred here. All right, thank you, Maya. Thanks everybody for joining us and for those who are still joining us. I'm James Markham with the Southwest EFC. Today we're going to be talking about activated sludge secondary wastewater treatment processes. We're going to cover some basics about components and operations, a little bit of microbiology, touch on some collection system variables, process controls, primary control points, and a few safety issues. This is part one of a two-part series on activated sludge. Part two, which will be presented by my colleague AJ Barney, who's been actively involved in this series, and you've probably heard before, is going to be in 2 weeks on October 11th. That's going to delve more into deeply into the activated sludge microbiology, cover abnormal operations, process troubleshooting, process modifications, and influent characteristics. So this initial session is basically to get you familiar with the terms, the basic processes, and of course, given the limited time that we have, this is not going to be an exhaustive description of these processes. It's really meant more as an introductory overview to supplement study of available resources from your state certifying agencies and other available resources that are out there, like the Sacramento State Wastewater Treatment Guides and other available resources. So with that, let's get started with a definition and a little bit of history. So activated sludge is basically the process uses microorganisms to convert dissolved solids and suspended organics into settleable solids that we can then take out of the wastewater stream. It's primarily designed for BOD removal, although it can be modified to remove other things. We're going to talk mostly about those modifications in part 2 of the webinar. Why do we use activated sludge? Same reason we do wastewater treatment in general. It's to protect receiving waters, right? If your wastewater system discharges into a body of water, there's somebody downstream, there's plants, there's wildlife that rely on that water, and we protect those receiving waters by removing suspended and colloidal solids to prevent them from creating nuisances in water bodies, so that the discharge, after clarification and disinfection, of course, is nice and clean, like this example from a system we work with down in Texas. We also do it to reduce biological oxygen demand, so that the waters aren't overloaded with oxygen depleting organics that can lead to things like low oxygen levels and fish kills, like this example from down in Florida. And we also do it to reduce disease-causing pathogens like bacteria and viruses and protozoa, internal parasites like Giardia and Cryptosporidia, things like typhoid fever, cholera, which is what you're actually looking at in that picture. And the process can also be used to remove nitrogen and phosphorus, depending on how it's modified. Again, we're not really going to dig into that aspect of ASPs today. That's a topic for part 2 on the 11th. But that's kind of our basic overall goal here, primarily getting rid of BOD and doing some nitrification. So what is the process? If you saw our fixed film webinar about 3 months ago, back in June. This slide's going to look kind of familiar because it's a very similar analogy. We're essentially ranching microbes, but in the case of the fixed film, we were growing those microbes on a film or substrate in an ASP or activated sludge process. They're free floating in the tank. So maybe a better analogy is like open range ranching, right? The activated sludge, it's full of organisms that are responsible for the decomposition of waste. They use the waste in the wastewater stream as an energy source for food, for survival and reproduction. And what we're essentially doing in a very balanced way is feeding the organics in the wastewater to those microorganisms. We provide a big tank as a home for them to float around in. The tank gives the microorganisms access to oxygen from the air because this is a predominantly anaerobic process. The food from the influent is used to grow and multiply, and their metabolism is what's actually treating the water, converting that waste into new growth, carbon dioxide, and water. And then, of course, we periodically cull the herd, so to speak, in clarifiers after the aeration tank by settling those dissolved and suspended solids out, which includes most of the microbes that are in there as well. We then feed some of that settled microorganism stock back into the aeration tank along with the primary effluent to essentially get a higher concentration of microbes in that stream than we normally would have, because everything that we're using in this process is naturally occurring in the wastewater stream. We're just increasing the concentration of microbes so that we get the wastewater cleaning performance that we want. Whatever we don't feed back into the system gets removed, dealt with as solids. We'll look at a flow diagram here in a minute. But biologically, the process is very similar to what we talked about in the fixed film webinar, with the major difference being that in activated sludge, again, everything, the microorganisms, the food are free floating in a tank, whereas in a fixed film process, we're growing the microorganisms on a substrate. Of course, as with all things with wastewater treatment, there are variations on a theme. There are some ASPs that actually have plastic substrate floating around in the tank. So they're doing kind of a hybrid system where they have some film growing on a media and some floating in the tank. But basically what we're talking about today is the free floating version. So activated sludge has been around for a really long time. Trickling filters or trickling beds were the first biological treatment that was developed back in around 1890. We talked about this in the fixed film webinar. This is sort of the first version of that. And although it did a good job of treating wastewater, there were some downsides. a major one being the footprint that you needed to actively treat the water. Some of these arrays were huge, covering acres and acres. Activated sludge was developed very shortly thereafter, early 1900s, and fairly quickly overtook trickling filters as kind of the dominant secondary treatment method because it had a lot of advantages at the time. Smaller footprint, better effluent quality, lower nuisance factors, so you didn't get as many problems with bugs and smells as would happen with these very large-scale trickling filters, or trickling beds as they were sometimes known. The point I'm trying to make here is that the process has been around for a very, very long time. It's very well understood. We'll talk about some of the basic variations today, and then more of those on the 11th. But it's a tried and true process. It's well understood, and it can be used for a lot of different things. So let's talk a little bit about the process components, and we'll do this sort of in the context of a wastewater flow schematic, so you can sort of see, if you're unfamiliar with this process, where it fits in. So typically, you're going to have plant influent coming into the plant. It's going to go through pre-treatment, and then primary treatment, where we're essentially going to be getting rid of, screenings and grit in the former, and primary sludge, the first sort of large portion of solids being removed in that primary treatment process. After primary treatment, the effluent from your primary clarifier starts its way through the activated sludge process. It goes into an aeration tank where we add oxygen, and what's left after the processing, and as you'll see, there's going to be a variety of different detention times depending on how you're running the system, goes into a secondary clarifier where the solids, again, are removed, and those solids go off to solids handling, except for part of it, which goes back into the system. And this is what makes an ASP an ASP. The activated sludge, called that because we're essentially a bunch of active microbes in the sludge that we're taking out of the secondary clarifier, get returned to the front end of the aeration tank. So that mix of primary effluent and activated sludge that's in the aeration tank is referred to as mixed liquor. And what we're essentially doing with this recycling process is increasing the concentration, the density of microbes in the tank so that they can treat the water the way we want it to be treated. What we don't need as RAS, or return activated sludge, gets wasted out to solids handling. That's referred to as WAS, waste activated sludge. That will be dealt with in a variety of ways, typically thickened, digested, dewatered, turned into solids, and any effluent generated from this process goes back somewhere into the front end of the treatment process as effluent, as part of an internal effluent recycle. Where that comes in kind of depends on your specific system. Of course, the supernatant from the secondary clarifier, the liquid part that we've separated the solids from, then goes on for further treatment, either tertiary treatment or more typically just to disinfection, and then gets sent out into receiving waters. So what's inside this box, that's the ASP, that's the activated sludge process. That's what we're talking about. Three main components: aeration tank, secondary clarifier, and a sludge recycling mechanism and wasting system. And as you can see, it's a loop process. And as an operator, you've got to balance all these different inputs: oxygen, food, RAS inputs for secondary wastewater, effective secondary wastewater treatment. So let's talk a little bit more about some of the specifics and what we're trying to accomplish here. So aeration is going on in the tank. If you're unfamiliar with it, it's basically the large scale version of what you're looking at here, or that you might see in your kid's tropical fish tank, or your own if you're like me and have one. We're basically introducing large amounts of air into the water by pumping it in through a diffuser like you see here in the fish tank. In commercial scale, they look kind of like this. And the goal here is to increase the oxygen saturation in the water so that the aerobic bacteria who need oxygen have enough oxygen to metabolize the waste that's in the wastewater stream. You can do this by diffusing oxygen through with blowers, like you see in the left here. It can also be done with large-scale mixers, basically a giant blender. Mechanical aeration device that splashes and mixes air into the wastewater and dissolves air in that way. With both of these, you're accomplishing two things. You're adding oxygen, so increasing the dissolved oxygen concentration, and you're also mixing the various components in the mixed liquor, keeping those suspended solids moving, keeping the bacteria and other microbes in there moving around so that they can do what they're supposed to. If you've never seen a diffused aeration system, the image on the left, that's what it looks like on the top. This is what it looks like on the bottom. Most common typical types of aeration systems have a pressurized air supply that blows air into a gallery of diffusers that are submerged at the bottom of the tank. That's those little round discs. You can see that piping network is what's sending the air to them. And those diffusers basically produce small bubbles that distribute air inside the tank and keep everything mixing. The air transfer increases the contact time with the wastewater, and the surface area of the bubbles obviously helps as well. The smaller the bubbles, the higher the rate of dissolved air you're typically going to get. And the goal here is essentially optimizing the contact time between the air bubbles and the wastewater to increase that DO. And of course, rolling patterns keep those bubbles submerged, and because this is all going on continuously, the solids don't settle, and you maintain continuous contact for that decomposition process to proceed effectively. After the appropriate detention time is reached, fluid is moving out into the clarification process, and the bacterial mass that has moved into the clarification process essentially stops growing because there's no food available here. The goal of this part of the process is capturing those biosolids as sludge at the bottom of the tank. There's a lot of different clarifier designs. We talked about some of them in our sedimentation webinar. They all more or less work along the same principle. You give the solids time to flock together and settle by slowing down the velocity of the water. It gets collected at the bottom, pumped out, and heads either back to the front of the aeration tank as RAS or out to solids handling as WAS. And then the clean effluent or cleaner effluent goes over a weir onto the following treatment stages. Then we've got the sludge waste and return system. This is sort of the end of a waste train down in Texas as well. It's a belt press. The solids are going to be dealt with in a variety of ways, again, depending on the setup of the system, thickening, digestion, dewatering, using something like this. But again, this is what's wasted out of the system. And again, we are wasting biomass out of the system in order to keep the concentration in the tank where we need it to be to digest the BOD that is coming in from the primary tanks. So we're not really using anything that's not already present in the wastewater flow. Those microbes are all naturally occurring. What we're basically doing with this recycling process is building up the concentration and keeping it so that we can essentially do a lot of decomposition work in a relatively short amount of time. So while we're talking about activated sludge here, let's look into some of the biological components in here. As again, I said at the beginning, primary goal with activated sludge is BOD removal and nitrification, depending on the age of the sludge and how it's processed. But those are aerobic processes. We're using aerobic bacteria, so bacteria that need oxygen to do the work for us. They do the heavy lifting, and this is, of course, why we're pumping air into the activated sludge tank or mixing it to increase that dissolved oxygen in the water. So aerobic bacteria, which are the vast majority of the bacteria and microbes that we're talking about here, they need oxygen. They grow relatively fast. They're very efficient waste oxidizers, and the good thing is they typically don't produce much, if any, odor as part of that oxidation process. The other kind of bacteria that you're going to have in here are what are called facultative bacteria. They don't need oxygen from the air. They prefer it, but they can typically live without it because they can strip oxygen out of compounds like nitrate, and sulfate when anaerobic conditions persist. So typically facultative bacteria prefer aerobic conditions because they can generate more energy in aerobic conditions, but they can manage just fine without oxygen, again, by stripping their oxygen they need out of other substances. Some of these are useful in wastewater treatment, others aren't. They tend to grow slower than aerobic microbes. And because, for example, they're stripping oxygen out of sulfate, they can produce unpleasant odors when they're in anoxic conditions, so low oxygen conditions. And typically, they're also less effective waste oxidizers than aerobic microbes. The image you're looking at on the right is E. coli, which is something that is very prevalent in wastewater treatment systems, and among other things, is actually a facultative bacteria. Other organisms that you're going to see in there, filamentous organisms, so organisms that look like filaments or strings. Having some of these in the system is just fine, and they're naturally occurring because they'll provide a support structure for other bacteria to flock on. But if these kinds of things dominate in the system, they cause problems because they don't settle well in secondary clarifiers, which results in poor effluent quality. And these things are often minimized using chemicals like bleach and polymer and flocculants, or sometimes even small reactors ahead of the aeration tank that create an environment to suppress their growth. So Nocardia, Thiothrix, Actinomyces, these are things that you're gonna see, but you're gonna be trying to keep control of. There's a lot of other stuff in there as well. Pretty much every wastewater treatment plant I've ever gone to has an organism chart on the wall because these organisms, these higher life forms, larger than the sort of single cell microbes that we're using primarily for the digestion, are really good indicator species. They're gonna be present, but which of them are present and the concentrations that they're present in correlate to plant performance. And I'm not gonna go into this in any detail. Again, this is a topic for the troubleshooting part 2, but it's good to know that there are a lot of other organisms in there that you're gonna be looking at on the daily, and they're gonna be able to give you indications of, the age of the sludge, whether you've had recent, high BOD loadings. They're basically your early warning system to help prevent critical upsets. Typically, these kinds of organisms are only going to make up, 4 or 5% of the biomass. But again, they're indicators. You have to keep track of these. And so microscopic analysis of your biological system is really a critical component of ongoing daily monitoring and control programs. And there's a fair amount of paperwork that goes with maintaining an ASP because those indicator species and other factors that we are going to talk about today are used to correlate the health of the system. So changes in flock structure, changes in the quantities of higher life forms, or the types of filamentous organisms are going to be determined by using a microscope and looking at the biomass. And again, those are going to be used to help determine what's going on in your system, for troubleshooting. So I mentioned that this is all essentially bacterial digestion. It's bacterial metabolism that's going on, that's doing the treatment for us. You can more or less think of it in terms of a basic equation like this, where we've got organic matter in the wastewater, we've got oxygen that we're adding, we've got nutrients as well floating around in there, we've got a bunch of microbes. You put that together, what do you get? More microbes, carbon dioxide, and water. At least when we're dealing with the BOD portion of this. We're also removing finely suspended materials that weren't removed in other stages, because the nice thing about flocculation is as those clumps get bigger, they drag things out of the water as they sink as well. So the food is the BOD here. And the tank is designed and operated in a manner to promote the growth of that bacterial mass that can flocculate or clump together in the clarifier, but to do it in a controlled way. So the bacterial digestion is essentially aerobic oxidation. We can think about this from sort of 3 perspectives. From the bacteria standpoint, it's like, I'm a bacteria, I've got oxygen, I've got food, I'm in a good place, I can live and multiply. From the operator standpoint, the operator has to track the strength of the BOD, or BOD strength of the waste coming into the process, so into the activated sludge tank, the actual sludge that's being returned into the tank and the concentrations we're maintaining in the tank, and of course the aeration. And then from a purely chemical standpoint, we're looking at electron donors, electron acceptors, energy, reproduction. No matter how you look at it, how you slice it, the end product's the same: oxidized wastewater, more bacteria, carbon dioxide, and water. Of course, as I mentioned, the primary goal here is BOD removal. Nutrient removal is also possible in an ASP. But you have to remember that, for example, nitrogen removal is a two-step process. The nitrification part of that, the aerobic bit, converts ammonia into nitrite and subsequently nitrate. Denitrification is an anoxic process. So that last step has to be done in some sort of a separate process, whether that's an anoxic process that's completely separate, or a portion of your tank that goes anoxic, so that latter step can happen. Conventional BOD systems, what we've been talking about mostly, and the diagram that I showed you, that have longer aeration times typically often result in nitrification as well, but that denitrification process is essentially a separate step that has to be done separately. So with that, we're coming to our first poll question. I have kind of talked around this, but not addressed it directly. If the strength of the incoming wastewater increases, so basically BOD goes up, what happens to the oxygen demand in the tank? Does it go up? Does it stay the same? Or does it go down?
Just so everybody knows, I'm going to leave these polls open for just about a little under a minute, and then I'll close them. All right, closing the poll in 3, 2, 1. All right, and the results are 92% said the oxygen demand in the aeration tank goes up, 0% said that it will remain the same, and 8% said that it will go down.
All right, perfect. So think about the definition: biological oxygen demand. If BOD increases, the demand for oxygen goes up, because more BOD means more food, which means more biological activity. And these are aerobic bacteria that need oxygen to break down the waste substances. So they're going to need more oxygen. In that situation, increased BOD basically means that the biological oxygen demand for molecular oxygen in the tank is going to go up. So good job. Let's talk a little bit about some operational variables, including BOD, dissolved oxygen, WAS, and a few others that you're going to have to be keeping track of. So as we learned from our prior question, the biological oxygen demand is how we refer to the food in the wastewater that the microbes in the ASP are eating. It's the amount of food left in the water coming out of the primary clarifier after a significant chunk of the solids have already been settled. So you're actually going to be tracking BOD in multiple places in the system, the very beginning, but also in the space between the primary and the ASP. It's the microbes food buffet, right? So strong wastewater is going to have high BOD, weak wastewater is going to have a low BOD, and you'll basically have to balance the oxygen inputs to manage that. And again, it's called that because metabolizing food by the bacteria requires oxygen. It's also good to note that generically, sort of food in this context is referred to as substrate sometimes too. So BOD or COD in an activated sludge process for BOD removal is going to be sometimes referred to as substrate, but recognize that substrate is kind of a generic term. So if you're talking about the nitrification process, ammonia nitrate and other reducing compounds are also substrates in those contexts. Oxygen is important, as we've said. This is primarily an aerobic process. Those aerobic bacteria need oxygen or they will die. Facultative bacteria won't die without oxygen, assuming there is some other place like nitrates or sulfates that they can strip oxygen from. But without dissolved oxygen, the aerobic bacteria will die, and then they become a problem. And low DO levels can actually result in septic conditions inside the tank, which we're trying to avoid. And then the sludge wasting process, so that combination of recycling RAS and disposing of WAS is what we're using to control the biomass in the ASP. This is really, really critical. You're going to adjust the wasting rate, essentially what you dump out of the system, based on the operational parameters of your particular activated sludge system. So how do you figure out what the biomass is? Well, you track mixed liquor suspended solids. So this is the combination of food and microbes and everything else that's suspended in your aeration tank. You'll do this in the lab using accelerometers. And the reason we track this is because if the solid content is too high, the sludge may bulk up. The treatment system can get overloaded. The dissolved oxygen content is going to drop because as those microbes are using oxygen to degrade the waste material, they're using up available oxygen. So if you got too many bacteria in there, they can and not enough oxygen, they're going to use everything that's available, which will effectively stop that part of the treatment. So can reduce the efficiency also of nitrification and sludge settling. And to combat that, you'll have to excessively aerate. That costs money because you're running pumps using electricity. On the other end of the spectrum, if it's too low, you don't have enough microbes in there to deal with the waste stream. You're going to have insufficient organic matter being removed, and the sludge age might not be old enough to do the nitrification portion if that's one of the things that you're going for. Good thing is there's a lot of indicators here. The color of the mixed liquor actually can give you an indication of plant performance in sludge age, and the food to microbe mass ratio, which we'll talk about here in a second. Ideally, it's going to be sort of chocolatey brown. If it's really light brown, that typically indicates or often indicates a low solids concentration or possibly over aeration or young sludge. On the other hand, if it's really dark brown or even black, that typically indicates that there's old sludge that might become septic with a low DO and high solids concentration. Because remember, we're growing bacteria in here, but they're also dying as well. So there's a little bit of a churn going on. So that's all of the solids in there, but we have to know what the biomass is. So we also track the volatile suspended solids. That's the amount of organic or volatile suspended solids in that mixed liquor. So it's going to be a portion of the other parameter. And it's approximately equal to the biomass in the mixed liquor suspended solids. It's not exactly that, but it's close enough to be used as an indicator. Why do we need to know this? Because we have to balance the biomass and the food. And we do that by calculating what's something called the food to microorganism ratio, FM ratio. In basic terms, it's basically the total rate of food applied to the aeration tank divided by the microbe biomass. So we've got a bunch of different variables that we have to keep track of, and that any system will track the flow rate into the tank, the BOD condition, concentration into that tank, the volume of the tank, and then of course the concentration of suspended solids in there and the portion of that is volatile suspended solids. This is reported as a mass over mass per day. So pounds of BOD over pounds of VSS, or kilograms per BOD over kilograms of VSS per day, as a convenience, because we'll see mathematically all the units except day actually disappear when we're doing the math. So I'm going to walk you through an example of this. So let's say this is our equation, and if we look at the units, you might think, oh, I have to do a whole bunch of conversions here, because I've got metric units and imperial units. I've got millions of gallons, but I've also got concentrations. So I can go ahead and use my conversion factors to end up with a result, but you really don't have to, because if you look at the units here, you've got millions of gallons top and bottom. This is, of course, assuming that your units are consistent. And when you're taking the test, a good thing to look out for is the fact that they will usually give you units that you do that are in different, something will be in millions of gallons, something will be in thousands of gallons, and you may have to adjust for that. But assuming that your units are the same, millions of gallons are on the top and the bottom of your equation. Concentrations are at the top and the bottom of your equation. And your conversion factors in this case are also the same on the top and the bottom of the equation. So you kind of don't need that middle part, because the only thing that's left over is days. Assuming your units are all the same, sometimes you can avoid the conversion and make the calculating process a little faster. The pounds over pounds per day or kilos over kilos per day is just a convenient way of talking about it, because if you think about it, we've essentially gotten rid of all of the mass values in our mathematical equation here. We use pounds over pounds or kilos over kilos because it's convenient. Quite frankly, we could use tons over tons, but that wouldn't tell us much because it's such a big number. So, mathematically, those units actually cancel each other out. We just use them for convenience. So, to do a problem like this, with some actual values, you might have noticed that the formula has volatile suspended solids in it. You're going to find that out in a lab. And so step one is going to be calculating the mass of volatile solids that make up the total suspended solids that you have in there. It's going to be typically a concentration, a percentage. So to figure this FM ratio out, my first step would be to figure out that volatile suspended solids. In this case, I know for my testing, it's about 85%, so 0.85 times 2,400 milligrams per liter gives me a VSS concentration in my tank of 2,040 milligrams per liter. And from here on, it's plug and play, because I've got all of my other variables. So my flow is 4 million gallons a day. My BOD concentration is 200 milligrams per liter. I've got the VSS that I just calculated. I know the volume of my tank, which gives me an FM ratio that I'm going to use as part of my understanding of how my system operates to determine whether I'm in the right parameters. What I'm trying to show you here, and again, we can't cover every parameter that we're going to talk about, is that there is a fair amount of tracking and lab work that needs to be done in order to maintain an ASP running optimally. You're going to have to keep track of BOD and DO. Things like pH, alkalinity, and toxic substances also have to be tracked, because those can have a big impact on the health of the organisms that you're trying to grow. Flow rates, obviously, you need to understand, because those are changing all the time, both diurnally and seasonally. And then, tracking the volatile suspended solids, the total suspended solids, lets you calculate things like the FM ratio. In typical lab results, you're going to see hopefully numbers in these ranges. These are some common ranges, but if you look at sort of the progression from influent to primary effluent to final effluent, and this is all assuming you're using a conventional ASP. As I said, there are variations on the theme. You can sort of see the change, primary influent maybe being in the 150 to 400 range, but the final effluent being in the 10 to 20 milligram per liter range. So we're going to track these things, BOD, the amount of suspended solids that dissolve, oxygen, and a few other things, again, to sort of track the performance of our system and make the appropriate adjustments. So I referred to earlier on about the fact that we can't discuss every type of ASP because we just don't have enough time, but I am going to go into some basic details about three sort of basic variations. I'm going to start with this table. There's a lot of different ways to classify ASPs. One of the ways of classifying them is based on loading rates. So we have what are typically kind of broken into three categories: low rate, conventional, and high rate loading. That basically involves the amount of food that we're loading into these systems. And what you'll see is that there's kind of an inverse proportion between hydraulic retention time and the volumetric loading and the food to microbe ratio. A low rate system has a long retention time, older sludge, relatively low volumetric loading and food to microbe ratio, whereas a high rate system has a lot of food being pumped in, very short retention times, and relatively high food to microbe ratios, and also short sludge age. And we'll see why here in a second as we go through some diagrams and discuss some of these parameters. So three basic variations. And again, there are a lot of different variations to ASPs. There's a lot of different modifications to the process that can be made, and there are a lot of different ways of classifying them. So depending on what resource you look at, you may find similar information being talked about in a slightly different way. You can classify based on loading rates, which is what I'm going to be talking about now, but you can also classify them based on fluid flow pattern or aeration method or reactor arrangement or solid separation methods, or whether you're doing biological nutrient removal as well. Again, a lot of variations on the theme, but we're going to keep it simple today. So what I've been showing you up to now is essentially the conventional, that mid-range volumetric loading option. Conventional plants are typically operated so that the amount of food is limited. The organisms are essentially required to compete for the available food, and they're typically characterized by sort of mid-range sludge age in the 3.5 to 10 or 5 to 15 day age. Kind of varies depending on the resource that you look at. Relatively moderate food to microbe ratio, relatively slow organism growth, hydraulic retention time of around 6 to 8 hours, but these result in relatively good effluent quality. So this is sort of a breakout of that table. So it's got this sort of mid-range retention time. There's also the high rate option. So this is the high food end of the scale, where we're pumping a lot of heavy load into the system. And they're typically used a little bit differently. And these are characterized by short retention times, fast organism growth, short sludge age, because since the organisms are growing quickly, you have to waste more of them to keep everything in balance, high FM ratio, and typically the output of these is lower than desirable effluent quality. Typically, this isn't something you would just send out to disinfection and out because you haven't dealt with all of the BOD in there. And that's okay, because high rate ASPs tend to be used in conjunction with a secondary ASP or other treatment. In this case, I've got one of the modified ones showing there that has an anoxic component to it that might be used for nitrogen removal. So things to remember here, high loading rate, short detention time, relatively young sludge age, and fairly high food ratios. And again, lower than maybe desirable effluent quality, but that doesn't matter because it's still in the treatment process, and there's going to be some process following this, maybe a conventional ASP, maybe one of the modified options that is going to do the rest of the treatment for us. The last example I want to talk about today is the low loading rate or extended aeration option. And this is quite often a setup that's used in smaller communities. And if you look at this diagram here, you'll notice something's missing, and that is the primary clarifier. And that's because the way these operate, they have relatively long or old sludge age, 20 to 30 days, low loading rates, and long detention times, sometimes up to 24 hours. So with these systems, you can often have sort of a net zero organism growth rate. There's not as much sludge wastage going on as in some of the other ones. Nitrification often happens in these as well, and they give very, very good quality. But again, because of the characteristics of these kinds of plants, these long retention times, sometimes they can be designed to not have a primary clarifier because the water, the waste is in there so long that it's taking care of essentially all of the biological material in there as well. These are typically suited for small community applications. They typically have very, very large aeration tanks and long aeration times. One of the other advantages of these low loading rates is that because the hydraulic retention time is so long, they can handle flow variations and shock loads a bit better than conventional or high rate systems can do. And again, as I said and showed in the diagram, sometimes they actually eliminate the need for a primary clarifier, and we just use a secondary clarifier operating at a lower hydraulic loading rate, but not always. So again, just to kind of look at the three of those things compared to each other, you can see, the difference in hydraulic retention time versus sludge age versus loading rate. They're essentially the opposite of each other. There are other ways to characterize tanks, as I mentioned. One is by design and process. There's sort of two versions that you see typically. Complete mix, which is what you're seeing on the left-hand side. That happens to be a mechanically operated one or mixed one. There are also versions of this that just have the diffusers in the bottom. And what's going on here is essentially because of the agitation and the mixing, you've more or less got an equal concentration of all the parameters all the time. So DO, BOD, VSS, TSS, pH, temperature, it's all more or less the same because there's constant agitation going on. The tanks are usually square or round, so you can kind of tell by looking at them what kind of tank they are. And again, the aeration can be mechanical like we're showing here, or it could be with diffusers. Other side of the spectrum is the plug flow. These are systems in which there is not really any lateral mixing going on after the RAS and the WAS are put together, and the fluid kind of moves through the system as a plug. They usually look something like what we're seeing here. They're long, narrow, rectangular channels. They might even be serpentined to get a longer track in a smaller footprint. And the thing about these is that the concentrations of various components are different at the beginning of the track versus at the end. So at the beginning, where the food and the RAS is introduced, the BOD and the oxygen demand, so the dissolved oxygen, excuse me, is going to be higher at the front end because that's where the food is and that's where the microbes are starting to do their eating. By the time the fluid gets to the other end, where the biomass has done its thing, there's less BOD, but a lot more biomass. And if you think about that, it kind of makes sense. They're kind of eating their way down the buffet, and by the time they get to the end, there's more microbes, but less food available. High aeration rate versions, like I showed you in the table before, can be done with a complete mix, activated sludge or CMAS, or a plug flow operation. The conventional ASPs that we've been talking about are typically done as plug flows, although again, there are variations on themes, and there are other kinds of systems as well. There's reactor-based things where things are happening in one basin, but different stages are happening at different times. But we'll discuss those in part 2 as well. So just to give you a visual, plug flow looks like this, more or less top down. We've got a primary clarifier on the left, we've got secondary clarifier on the right, and the fluid follows a pattern through the serpentine, starts out again with fewer microbes and a lot of food, and ends up with a lot of microbes and less food. There are variations on this as well. You can have, all of your BOD going in at the head of the clarifier. Some do step feeds where they're feeding, some of it in different stages. But a plug flow basically works like this, where the fluid is moving through the system kind of as a consistent slug. Taking a side view this time, complete mix, basically big square or round basin with an agitator in there that's going the full time, that's mixing everything up. So again, 2 variations on a theme, but as with everything in wastewater treatment, it seems, there are multiple variations. One you might be very familiar with is the oxidation ditch, which is actually a combination of those 2 processes. So if we look at this, you can see it. This is 2 of them side by side. Those aren't actually connected. At either end, we've got a complete mix portion going on, whereas in the middle, we've got these tracks where there's essentially plug flow going on. The flow is about 1 foot per second. The agitation is slowly moving this water around. So you've got a combination of both kinds of processes going on here. So talked about volatile suspended solids. Another thing that you're going to keep track of is the age of your sludge, or sometimes looked at as the solids retention time or the mean cell retention time if you're just looking at the cell mass in the sludge. All of these are essentially the average time that solids are retained in your aeration tank, and you calculate that typically in terms of days, and it's just the mass of the solids in the tank, which you can get by calculating the concentration over the volume, divided by the mass rate of solids entering the tank. So again, this is why we're tracking what's going on in the tank and also what's in the fluid coming into the tank. This is one that you are going to calculate for me, so pay close attention. The SRT is essentially the volume of the tank times mixed liquor solids divided by the flow going out times the solids going out as WAS, and the flow of the effluent and the solids in the effluent going in out of the secondary clarifier. And there's a lot of different ways to calculate this based on your setup, because if we looked at the low rate and the high rate version, we've got multiple tanks. We've potentially got a lot of solids in our clarifier or very little in our clarifier. So you have to know something about your setup to determine which pieces you're going to include. So for example, this is taking account of the solids that are in the secondary clarifier, assuming that that's going to be a relatively large component. If you've got a sludge system where sludge gets pumped out of the secondary clarifier pretty promptly and there's only minimum solids in there, you might leave that secondary clarifier term out of the equation. So that equation would look like this. You can see the top right-hand term has disappeared. Again, don't arbitrarily change how you calculate this at your plant based on this webinar. Your calculation is going to be based on your specific setup, but just realize that what you're keeping track of are flow and mass in the system. So you have to define what that system is to calculate it correctly. So what I'm going to do is I'm going to give you some elements here. We've got a volume of the tank. We've got a flow into the tank, 4 million gallons per day. We've got a flow of WAS out of the tank, 0.075 million gallons per day. We've got a mixed liquor suspended solids of 2,400 milligrams per liter. And then we've got total suspended solids in our WAS and our effluent of 6,200 milligrams per liter and 12 milligrams per liter as well. So I want you to take this information, plug it into our equations, and give me an answer on how old the sludge is, or how old the solids are in this particular setup. And that first formula under there, the QF equals Q minus QWAS, that's your first hint, because you have to figure out what the flow of the effluent is, and that's going to be the flow into the tank minus what we're taking out in the form of WAS. So Maya, if you can throw the poll question up. The formula is there. It should be more or less plug and play. We'll give you a couple of minutes here to figure this out, and then we'll see where we're going. And once we're done with people answering it, I'll walk through the equation just so that everybody understands how we get to the appropriate answer.
Just gonna give it a few more seconds here. Also, if the poll here is blocking any formulas for you, you can open up the handouts tab and pull up the slides and have them alongside as well.
Yeah, and you can drag and drop that poll around. So if it's in an inconvenient place on your screen, you should be able to grab it and move it.
All right, just gonna give it a couple more seconds just to get more votes in here. All right, I'm gonna close it in 3, 2, and 1. All right, so the results are for the question, what is the solids retention time for the given variables? 65% said 4.7 days, 26% said 0.4 days, 7% said 5.7 days, and 2% said 0.1 days.
All right, well, the majority of you got it right, so that is a good thing. Let us walk through this equation and show you how we got there. So the answer is 4.7 days. Again, the first thing you got to figure out here is what is the effluent flow out of the secondary clarifier. or out of the clarifier, and that's just essentially your flow into the system minus the flow that we're wasting. So you've got the flow that we're wasting and the flow that we're going into the system right here. So that's the thing that you use to calculate the one missing variable that isn't listed here. That gives us 3.925 million gallons per day. From this point, we can essentially plug and play this. It's 1 million gallons, so the volume times the total mixed liquor suspended solids divided by our QWAS times the concentration of solids in that WAS, which is obviously going to be very, very high because that's our effectively collected sludge at the bottom. It's going to have a high solids concentration. And to that, we add the effluent going out of the system and the concentration in that, which should be very, very low because, again, we've gotten rid of most of the solids. You put that together, we look at our units, make sure that those cross out, and what we're left with is days down at the end. And if you run that through your calculator, you end up with 4.7 days. If you chose 0.4, you probably added all the bottom terms together without doing the multiplication. If you picked 0.1, you multiplied everything across the bottom instead of multiplying the two sets of brackets separately. So the QWAS multiplied first, this multiplied second, and then those two pieces added together. The SRT and the WAS weight of removal are going to be inversely proportional, right? So if you're putting in RAS into the system to increase the concentration in there. So if you want to increase the solids retention time or how long things are in the system, if you want to decrease that, you have to increase the WAS removal. The more you take out of the system, the shorter the solids retention time is. The more you leave in the system, the higher the solids retention time is going to be. And of course, that's going to be limited by the fact that things are continually growing in there and you don't want to plug everything up. So again, as with the FM ratio, the reason that we're calculating these things is there are a lot of different design characteristics that are related to each other that you have to track to verify that your system is working the way it should. And you can also use these various characteristics to determine how a change is going to impact the other parts of your system. So we actually talked about 4 different processes. We talked about high rate, conventional flow, and extended aeration. We also showed you the oxidation ditch, so I threw that in there as well. So, these can be done with different reactor types. All except for the conventional are typically done with one or the other of the 2 kinds of reactors that we talked about. Although with the oxidation ditch, notice it's CMAS or complete mix and plug flow because of different things going on. But again, you've got a difference in SRT. So in our last example, assuming we were a plug flow system, that 4.7 is at least within the right range for a typical conventional plug flow system. But of course, your mileage may vary. Your system is going to be set up, and during its startup process, specific ranges will have been dialed in. So 4.7 is in the sort of general right range, but it might not be quite the appropriate range for your system, in which case, if it's too high or too low, you're going to have to either increase or decrease that WAS. Again, there's a lot of operational parameters that you have to keep track of, so you'll have to dial in based on what your system actually needs by increasing the wasting rate to decrease the age, or decreasing the wasting rate to increase the age. So we've got a few minutes left here. I'm going to go over some quick variables outside the plant and inside the plant that are going to affect your processes, and then we'll talk a little bit about safety considerations. So collection system variables, everything is dependent on the BOD, the strength of the wastewater coming in and the flows coming in. Wastewater is typically going to come from a variety of different sources, domestic, commercial, and industrial, and each of those have different changes in water use, diurnal, weekly, seasonal. how much water people use directly impacts how much wastewater is flowing through your collection system and going into your plant. They're all going to change. They're not necessarily going to change equally or in step. The wastewater characteristics also change as they move through the collection system due to pollutants and chemicals that might be added by, for example, industrial customers, or blockages that might cause some of your water to go septic. I&I infiltration into your sanitary sewer system can increase flows into the plant during storm events. If you've got a combined sewer system, not only storm events typically impact you, but spring thaws are typically going to result in increased flows, which could hydraulically overload your plant. And as I mentioned, collection system blockages can lead to septic wastewater or plugs of septic wastewater coming through and hitting your plant and causing shock loads. All of which basically means you've got to keep in contact with your collection system crews so you know what's going on out in the field and can anticipate what's coming through you. If you've got a pre-treatment system, you've got to keep in contact with staff that are involved in the pre-treatment program so that you know what's going on out in the collection system so that you can anticipate and adjust. Of course, all of those things are going to result in changes in the influent characteristics, and we'll talk a little bit more about this in round 2, but BOD, COD, TSS, VSS, total nitrogen, ammonia, nitrate, phosphorus, pH, alkalinity, all of those things, or changes in all of those things, can affect the operation of an ASP. Some of them very little, some of them very much. So, plants are designed with specific ranges in mind, so those characteristics have to be monitored, and we'll talk again a little bit more about that in part 2, but realize that you've got to monitor those processes and adjust to changes. You also have to pay attention to internal cycle flow changes, because those can impact as well. Dewatering processes, the effluent from that, from the solids, goes back into the loop. You've got to be able to account for that. One big thing that can be a concern is sewage haulers. So septage from hauling trucks are typically very small volumes overall, but they're really variable in terms of their source and their quality. They might even have, toxic or inhibitory substance in it. If you think about it, music festival that's been going on for a week, there's a bunch of porta potties out there. When that's collected, it's probably not going to be in the greatest shape. So if sewage hauling is an important part of your processes, you need systems and protocols to deal with those. Some plants have permitting systems and typically have lab checks to test the quality and quantity of the sewage haul that's being hauled in, so that they can adjust accordingly. Again, not an exhaustive list of things to think about, but scratching the surface here. And of course, there's always safety considerations. We've talked about these in the context of other webinars as well. A big one is drowning. These are big tanks full of liquid, and I can't repeat this enough. Aeration really reduces the buoyancy of the water. So, although if the water were still and you fell in, you might sink. If it's heavily aerated, and there are some really high volume aeration systems, there's a very good chance if you fall in, you're going to sink to the bottom. And unfortunately, there's all kinds of equipment down there that you can get hung up on. So you really don't want to fall into one of these tanks. You want to be careful about slippery edges. You want to make sure that the guardrails are in place, and that if you're working with a system that doesn't have guardrails, you've got a flotation device or life jacket on when you're working around these. You should also have Coast Guard approved life preservers with permanently attached hand lines at strategic points around the tank, just in case somebody does fall in, so you can throw that to them. Good rule of thumb, have them no more than 200 feet apart, have about 90 feet of hand line per preserver. The idea is that you don't want to throw the ring in there and then not be able to pull the person out. And of course, most ASP tanks have got some kind of electrical equipment associated with them, blowers, mixing equipment. A lot of it's automated. Just because it's off now doesn't mean it will be in 5 seconds. So when you're working on moving equipment, working with electricity, make sure you use those lockout and tagout procedures we talked about in earlier webinars to ensure that equipment doesn't accidentally get turned on and injure you or a coworker. And then last but not least, wastewater. There's lots of pathogens in there. We talked at the very beginning about pathogen removal. working with wastewater, particularly water in an ASP, means potentially coming into contact with pathogens. Nobody wants infections, so make sure you maintain proper hygiene, wear the appropriate PPE when you're in the plant in general and when you're near the activated sludge process in specific. Read and understand those chemical data sheets for chemicals that you might be using, and always know where the nearest eye wash and shower stations are so that if there is an accident, you can get cleaned up really fast. And on that note, every plant should have a safety program and detailed emergency procedures. If your plant doesn't, now is a very good time to get started on those. And once you have them in place, it's good to do some dry runs and test runs to make sure that everybody knows how they work and what they're supposed to do in the event of an emergency. So I apologize, we've gone a little bit over time here. I'm not sure if we have time for you all to stick around for Q&A. We will try to answer any questions that may have come in, but if we can't get to them, we will do that in a follow-up email. It tracks all the questions that people have put in. So we'll open the floor now. And I do want to again point out that we have regular office hours. If something in any of these webinars piques your interest and you want to talk about them, or you have a question that you think we might be able to answer, feel free to reach out to us. We've kind of set aside an hour every Tuesday with the various time zones listed there. You can email AJ or email me, and we'll set you up with a Zoom meeting and talk to you. So there's our contact information. And here's a nice picture of our logo. So with that, did any questions come in? We'll see if we can answer them if they did.
There is so far one, and the question is there an optimum or ideal ratio of RAS to WAS?
It's going to be entirely system dependent. Typically, the ideal ratio is going to be determined, or the range that you want to stay in is going to be determined during the startup procedures. The plant's going to be designed to do a specific process within a specific range. There is a little bit of trial and error sometimes that happens at the beginning of a plant startup where you sort of dial that in. But again, you have to realize that and having an ideal WAS to RAS ratio would be great if nothing on the front end changed, like if your wastewater stream was constant, but it's not. So, there's going to be ideal ranges for specific circumstances. I know that's probably not the answer that you were looking for. Unfortunately, ASPs are not really kind of a set it and forget it kind of process, because you're constantly having to balance all these inputs, and we're dealing with microbial growth. Things like the temperature of the tank are going to impact growth. When it's colder, things grow slower. When it warms up, they grow faster. If it gets really hot, that can impact growth as well. So there are a lot of variables that you have to track. So there isn't going to be an ideal ratio that you can use at all times. There will be a range that is correct based on the type of system that you have, but that is largely a function of how it's designed, what processes are coming before it, and what processes are coming after it.
That looks like the only question that we have at the moment.
Okie doke. Well, thanks for sticking with us. I realized we went over. I apologize for that. You've got our contact information there. This is what we do for a living. If you've got questions, feel free to reach out. The funding that provides these trainings also provides technical assistance. So if you've got a thorny question that you want to talk about, feel free to reach out to us. We can usually do that for free. We're your tax dollars at work. We're a resource available to you. And if we can't figure out the answer, we can usually find somebody who can. So with that, I will wish you a good rest of your day. Thank you for joining us. And please come back on October 11th for part 2. Again, I think that's going to be really useful and maybe perhaps more useful for the folks in the audience who have some experience with this system, who aren't just sort of learning about the different parameters, because we're going to be talking about abnormal operations, troubleshooting, indicator species, and things like that, that you're going to use to actually make changes. So please come back on the 11th. And for the rest of the webinars in this series, this is going to be going on through January or February at least. Thanks for joining us. Have a good rest of your day.
And thank you, James, for sharing your expertise with us. As noted before, you can find the handouts tab on your control panel, and right in there will be the PDF of the slides from today. But also after this webinar, you will receive a follow-up email with the slides and also a link to the recording. We also ask that you complete the webinar evaluation following the webinar today, so you can let us know your thoughts on today's session, as this helps us plan future webinars on topics that are important to you. Thank you all again. Thank you, James, and we hope to see you at future EFCN events.
Thanks again. Bye-bye now.